700 feet above Manhattan, a 2-ton steel beam swings through empty air. The year is 1913. Below, horse-drawn wagons dodge trolley cars while pedestrians crane their necks upward. Above, men balance on 12-inch wide girders with nothing between them and the street but skill and nerve. Watch that beam closely. It left a Pittsburgh mill 3 weeks ago as molten steel, was rolled to exact specifications, traveled by freight car across Pennsylvania, got unloaded at a Hudson River rail yard this morning, and rode a horse-drawn wagon through morning traffic. Now it's 700 feet up, swinging in a 15-mile-per-hour wind, guided only by hemp ropes and hand signals. This is how they did it, at a cost measured in lives. And understanding the method reveals not just extraordinary engineering, but a bargain with death that would eventually change how we value human life itself. Before the 1880s, buildings were prisoners of their own weight. Stone and brick walls had to be thick enough to support themselves, and that thickness increased with every floor. By the time you reach 10 or 12 stories, the ground floor walls might be 6 feet thick, swallowing up rentable space and making taller construction economically pointless. The Monadnock building in Chicago, completed in 1891, demonstrated the limits. At 16 stories, its masonry walls were so thick at the base that they consumed nearly a quarter of the ground floor. This was as far as stone could go. But the Bessemer process, perfected in the 1850s and refined through the 1870s, changed the equation entirely. By blowing air through molten iron, the process removed impurities and created steel that was both stronger and more consistent than anything available before. Suddenly, American mills could produce steel beams by the thousands. Each beam could carry far more weight than stone at a fraction of the mass. A steel column 12 inches square could support loads that would require a masonry pier 4 feet across. This created a revolution in architectural thinking. Instead of load-bearing walls, engineers could design steel skeletons, frameworks of columns and beams that carried the entire weight of a building down through precise connections to bedrock foundations. The walls became curtains, hung on the skeleton like clothes on a frame. They no longer bore any weight beyond their own. This freed architects to use lighter materials, larger windows, and to build higher than ever before. By the early 1900s, the race was on. The Manhattan Life Insurance Building reached 348 feet in 1894. The Park Row Building hit 391 feet in 1899. The Singer Building pushed to 612 feet in 1908. The Metropolitan Life Tower reached 700 feet in 1909. Each building held the tallest title briefly before being surpassed. Then came the Woolworth Building. Completed in 1913 at a cost of $13.5 million, it soared to 792 feet, 60 stories of neo-Gothic grandeur designed by architect Cass Gilbert. It would reign as the world's tallest building for 17 years. Its frame alone consumed 24,000 tons of structural steel. Every piece custom-made at mills in Pittsburgh and Gary, Indiana, according to specifications that filled hundreds of engineering drawings. But getting all that steel from the mills to the skyline and assembling it with precision at heights where a single mistake meant death required solving problems that had never existed before. Manhattan in 1910 was already one of the most crowded places on Earth. Streets choked with traffic, buildings pressed against buildings, and absolutely nowhere to store construction materials. Steel orders took 3 to 6 months to fill. Each beam was rolled to exact specifications, specific lengths, specific shapes for specific positions. A column for the 45th floor might weigh 3,000 pounds. A girder might measure 40 feet and weigh 2 tons. Every piece was unique. They were loaded onto freight cars, arriving days later at rail yards along the Hudson or East River. From there, the challenge became almost impossibly complex. There were no vacant lots, no storage yards. This forced a radical approach, just-in-time delivery, 7 decades before the term was invented. Wagons would thread through traffic, delivering beams straight to the curb. Workers immediately attached each piece to a hoisting system. Within minutes, that same steel would be rising into the air, swinging over trolley wires and lampposts to reach iron workers above. Every shipment had to arrive in perfect sequence. If a beam showed up out of order, there was nowhere to put it. Work stopped. On major projects, dozens of deliveries arrived daily. One delay rippled through everything. Foremen lived in constant fear that a single disruption would cascade through the schedule. The machine that made it all possible was something most people have never heard of: the Guy Derrick. Picture a tall mast, 50 to 75 feet high, mounted vertically on the building's steel frame. 4 or more steel wire ropes, called guy lines, stretched from the mast's top down to anchor points on the frame or the street below. These lines held everything steady against wind and shifting weight. From the mast's top extended a boom that could swing in a complete circle, picking up loads from the street and placing them anywhere within reach. The power came from steam. Boilers fired up hours before dawn, feeding pressure to hoisting engines that turned drums, winding up wire rope more than an inch thick. A single steam hoist rated at 50 to 100 horsepower could lift 10 tons straight up. Setup required extraordinary care. Every guy line had to be tensioned perfectly. Too loose and the mast would sway, too tight and it could buckle. Workers used plumb bobs to check that the mast stood perfectly vertical. Each anchor point had to withstand forces of 20 or 30 tons. As the building grew, the derrick had to climb with it. Every few floors, crews would jump it, unbolt the base, slacken guy lines while keeping others tensioned, then use an auxiliary hoist to lift the entire mast up to the next level. The mast would hang in mid-air for heart-stopping minutes before settling onto fresh beams. Each jump could take half a day and required perfect choreography. At least 3 guy lines remained under tension at all times. On large projects, multiple derricks worked simultaneously at different heights, their loads swinging past each other in sequences that demanded split-second timing. 300 feet above the street, 2 connectors wait on an I-beam flange 12 inches wide. A beam swings toward them, guided by tag lines. They pull the ropes, twisting the steel into position, reading its movement like sailors reading the wind. A gust sends it swinging like a 2-ton pendulum, but these men move with practiced calm, their bodies automatically adjusting for balance. The beam settles onto the column tops. Now comes precision work. They hammer drift pins, tapered steel rods into the holes, forcing the heavy beam into perfect alignment. The clang echoes across the frame. This takes 20 minutes. Every hole must line up exactly. Temporary bolts hold the joint, but the permanent connection comes from rivets. The riveting gang is 4 men, 1 organism. The heater stands at a portable forge, pulling cherry red rivets from flames at 1,800 degrees. With tongs, he arcs a glowing rivet through the air, sometimes 20 feet, sometimes 30. The catcher tracks it, snatches it from the air with a blackened bucket. He has 10 seconds before it cools. 1 fluid motion, jam the hot rivet into the hole. The bucker-up braces a heavy steel bar against the rivet's factory head, leaning his full weight into it. The riveter presses a pneumatic gun against the glowing shank and pulls the trigger. The gun roars, 1,000 blows per minute, flattening the rivet in 10 to 15 seconds into a perfect mushroom dome. Each rivet must be driven before it cools. A single beam connection needs 12 to 20 rivets. On a good day, a gang drives more than 500. The sound rings out like a metallic heartbeat. Clang, hiss, roar, clang, hiss, roar. The sequence repeats endlessly, rivet after rivet, connection after connection, beam after beam. The building grows 1 joint at a time. There were no safety harnesses, no nets below, no guardrails, no hard hats, nothing. The leather body belts available weighed 8 to 10 pounds and had a fatal flaw: no leg straps. If a worker fell, the belt would ride up, crushing internal organs, or flipping him upside down. Suspension trauma could kill in minutes. Ironworkers had seen this happen. They believed the belts were more likely to kill them than save them. So they relied on something else: skill, communication, and an unwritten code. Voices vanished in the roar 300 feet below. Crews used hand signals. One hand raised meant hoist. A wave directed the load. A flat palm meant emergency stop. A fist in the air meant danger overhead. The signalman was the only person who could speak to the hoist engineer. No one else interrupted. Workers never went on the beams alone. The buddy system was absolute. If a man slipped or froze, someone had to be close enough to help. Many of the most skilled ironworkers were Mohawk men from Kanawake. Starting in the 1800s, they'd built an international reputation for fearlessness at height. By the 1910s, whole Mohawk families had relocated to Brooklyn. Their cultural tradition treated the work with respect, but not fear, a psychological advantage hundreds of feet up. Lunch happened right there on the frame. Men sat with legs dangling over empty air. There was nowhere else to go. Wind was the constant enemy. Above 40 miles per hour, all hoisting stopped. A 2-ton beam could swing 15 feet in a strong gale. During one November 1911 storm, wind speeds jumped from 25 to 55 miles per hour in seconds. Workers lashed everything down. The site shut down for 2 days. Falls were common, not occasional. Common. Contractors calculated a grim formula: 1 worker death for every $1 million spent. On a $13 million project, that meant budgeting for 13 deaths. This was actuarial reality, built into budgets and insurance bids. The Empire State Building's official record lists 5 deaths. Union accounts suggest 8 or 10. Many deaths went unreported, especially non-union workers or recent immigrants. Casualty records are incomplete. Widows' funds, established in 1906, offered families $300 to $500, raised from workers' own pockets. When a man fell, his name might appear in a brief newspaper notice. John Murphy, 34, ironworker, fell from the 28th floor. Death was instantaneous. Sometimes not even that. The work continued. The next day, someone else took his place on the beam. Despite the danger, the pace was extraordinary. Major buildings rose at 1 story every 3 to 4 days. The Woolworth Building's steel frame went from ground to 60 stories in less than 6 months. During peak periods, entire floors could be framed and decked within a week. This required meticulous planning. Engineers calculated loads to the pound. Structural plans ran to thousands of pages. Foremen tracked which wagons carried which beams, which sections were ready, which crews were ahead or behind schedule. A good foreman could visualize the entire structure in his head, knowing beam K47 connected to columns J and L on the 32nd floor, and had to be placed before K48 and K49, which had to happen before the riveting gang could work across that section. Skilled connectors could glance at identifying marks, NE32G4, and know exactly where a beam belonged. Riveting gangs moved with machine-like efficiency. But speed came at a cost. Contractors faced financial penalties for delays. Investors wanted buildings finished and generating income. The pressure flowed downhill. Light rain, keep working. Wind at 35 miles per hour, that's below the 40 miles per hour shutdown, keep hoisting. Crews worked 10 to 12-hour days, 6 days a week. The culture prized toughness above all. Men who complained were mocked, reassigned, or fired. The buildings rose through brilliant engineering, ruthless logistics, and the willingness of working-class men, many recent immigrants, to risk everything for $7 to $12 a day. The Guy Derrick method persisted into the 1950s before tower cranes gradually replaced it. Those modern machines could lift heavier loads with greater safety, but required ground space and setup time that 1910s Manhattan didn't have. The real legacy isn't the equipment, it's what those deaths eventually forced: change. Union pressure, public outcry, and the sheer human cost led to the first safety regulations, the first requirements for protective equipment, the first acknowledgement that no building is worth a man's life. Today's construction workers have hard hats, modern harnesses that weigh less than 3 pounds, safety nets, and regulations. Deaths still occur, construction remains dangerous, but the rates are a fraction of what they were. Every safety regulation exists because of the men who died building those early skyscrapers. Their sacrifice changed how we think about work, risk, and human life. The coordination methods developed then, signaling systems, careful sequencing of deliveries, became foundational to modern construction management. But the most important change is invisible. We no longer accept death as an inevitable cost of progress. When you walk through Manhattan and look up at these towers, you're seeing monuments to human ambition. But you're also seeing graves. The exact number who died will never be known. Their names weren't always recorded. Their families received pittance. The buildings rose, became famous, changed cities forever, while the men who built them faded into anonymity. But their legacy is everywhere. It's in every safety regulation, every harness, every hard hat, every worker who goes home alive at the end of the day. It's in our understanding that no deadline, no profit margin, no architectural vision is worth a human life. The towers remain. The methods are obsolete. But the lesson endures. Progress built on the backs of the disposable is not progress at all. It's just a monument to what we were willing to sacrifice before we learned better. That is how they built skyscrapers without cranes in the 1910s. And that is why we must never forget the cost.